All right, welcome everyone. Thank you for coming. This talk today is about developing and deploying your next AJAX application to the cloud. And I want to talk a little bit more about Google Web Toolkit and Google App Engine. This is somewhat of an introductory talk, so if you're new to web development or would just like to learn more about the basics, this is the right talk. If you're looking for very advanced talk, it's probably better to visit the session later this afternoon. This is our agenda for today. We're going to talk about focusing on users first, talk about some of the challenges, reliability and scalability. We'll do a little introduction of Google App Engine. Then we'll talk about Google Web Toolkit, modern web application development. We'll talk about why we select Java as a development language. Of course, we want to make the point that faster is better than slow. We talk about developer productivity. And then a little bit about compiler magic that GWT does for you. And we should have some time for questions. Also today, there'll be office hours outside. I'll be available for both Google Web Toolkit and Google App Engine. And feel free to come by and ask questions. So web development. The basic setup is we have users who use a web browser to interact with applications in the cloud. And those web browsers need user interfaces. And we have a product for that I'd like to talk about, which is Google Web Toolkit, which allows you to build great user interfaces. The other one I want to talk about is Google App Engine, which helps you deploy these applications to the cloud. So users first. This is something that we've learned at Google. If you put users first and think about users first and foremost, all else will follow. One of the most important things we've found is that being fast is very important. Even when users don't realize it. They might not know that they want a faster application, but the data shows that when you make an application faster, users use it more often, they use it longer, they're more sticky to the application, and they learn faster. So I make that point again, don't be slow. Don't create a slow application. Create a fast one. And at Google, we also focus a lot on actual measurability, because many of us think we know what's the right decision, what the right design choice is, what the right option is, but we found that oftentimes we're wrong. And the only data that's true is the users using your application. So I encourage you to take your data from your application, take actual usage data and plot it. Put it in a graph. Compare it. Run experiments. Try a user interface shape A and try version B. And then compare the two and see which one users use more often or which ones they use better. Embrace asynchrony. What that means is the web is an asynchronous platform. When you send a message from the browser to the server and wait for a server to respond, that can be a long time. Long enough that if you waited for it, it would block the user interface and give a very poor experience. So just embrace that. Understand that anytime you talk from the client to the server, it's an asynchronous process and it may not happen immediately. And when you do that, your application design in the client actually becomes a lot easier when everything is deferred. And maybe a last tip is don't recreate the desktop experience. Just because it works on a desktop doesn't mean it's the right thing for the web. Try to think of a new UI, a new user interface that works for the web experience. Now, why does speed matter? If we just look at the way humans perceive changes in the world around them, we discovered that about 100 milliseconds is the shortest amount of time that a user can perceive a change. So if something happens faster than 100 milliseconds, we see it as instantaneous. It just happened. As soon as it's longer than about 100 milliseconds, you can start to detect the change. There's a short delay when you click on something before something else happens. So you always want to keep any user interaction under 100 milliseconds. Now, once you've reached about a second, the user can start to feel disconnected. If I click on a button and it takes more than 1 second for a response to happen from the user interface, then I'm not sure if that happened because I clicked or it happened for some other reason. And so that's kind of disconnected. So you definitely don't want to go there. When you reach about 10 seconds, the user's lost their attention and they're moving on to a different website. Now I want to take a moment to talk about some of the challenges of developing for the web, or really any distributed system. Think about it. You have users all over the world that can access your application from anywhere. And just due to the distance, you have to think about the distance that the client is from the server and the amount of time it takes. So let's talk about some of the sources of slowness that you don't control. The first is bandwidth. How much data can the user receive? How fast is the internet connection that they have? The second thing that you don't control is the number of connections that the browser can make. Each web browser is limited to the number of simultaneous connections it will create with the server. But the biggest one that many people don't look at, and this is really what I want to point out, is that latency is the biggest driver behind slow applications. And I'll go into a little bit more detail. But really think about latency when you're building your application and what it does. Now, I talked to you about the number of connections. This is from Steve Sauer's website, blog. And you can see there that depending on the web browser, there's a different number of connections that the client can create with the server at the same time. This is per host name. So if I'm connecting to www.google.com, then that web browser can only create in, say, Firefox 2 connections. But in Firefox 3, you can create 6 connections. So you can have 6 simultaneous image downloads or HTTP requests. Now I want to talk about those round trips. Before I came to Prague, I worked from the headquarters in Mountain View, California. I just wanted to see what the distance was like and what the latency was like. So I put Prague on the map and I put Mountain View on the map and looked up the distance, and it's roughly 9,500 kilometers. So I can, in Google, I can just type 2 times 9,500 because I have to go there and back, divided by the speed of light. And Google tells me that a beam of light shining from Mountain View going to Prague and back should take about 60 milliseconds, 63 milliseconds here in this case. So that's the fastest you could create a communication link. The reality is much slower. The fiber cables that connect the cities don't always pass in a straight line. There's many interconnect points where the light data has to be converted to electric and back to light and back to electric. And there's other equipment along the way that makes it slower. So here I'm just pinging a site in Prague, and I see that there's about 160 milliseconds round trip. So that's not very much. 160 milliseconds, that's 1/10, 1/20th of a second. That's 1/10, 1/5 of a second. That's pretty fast. But now think about all the steps that happen when you enter a URL and you visit a website. There's first a DNS round trip, because I typed in the name of the website. It needs to be translated to an IP address. Then the web browser has to set up a TCP IP connection. So it has to open up a connection from the client to the server on port 80. So that requires sending a packet to the server and the packet replying back that the connection is now open. After the TCP connection is set up, the browser can set up an HTTP connection, so make a request. So then it sends a packet to the server and says, I'd like to get this web page, and that page comes back. Now, if the web page has a redirect on it, because I didn't add a slash at the end or because I'm going to index.html, that's another round trip to the server and back. So now we already have 160 milliseconds, 160 milliseconds, 160 milliseconds. And the user hasn't seen anything yet. Now, for every image on the page, 160 milliseconds. For every CSS resource, 160 milliseconds. For every JavaScript file that you mentioned on the page, 160 milliseconds. And you can see how this quickly adds up to maybe thousands of milliseconds. That means there's several seconds before the web page is fully loaded and displayed on the user interface. Now, I pointed out the things that you don't control. You don't control bandwidth, you don't control number of connections, and you don't control latency. But what you do control as a developer is the number of round trips. If you can take some of these images or CSS resources or JavaScript files, and you can combine them into one file and make it one HTTP round trip, you can make an application noticeably faster. And that is an area where Google Web Toolkit makes it very easy to combine these resources and do it in a very efficient way. Now, if you create these applications, you need servers to run them on. And we realized at Google that it was really much too difficult to build out services. In fact, you spend so much time building services that maybe you have to configure machines and databases, and you spend all this time dealing with that instead of building the application and providing support to your users. And ultimately, your users pay for that. There's idle capacity that is lost when your servers aren't being used. You have to apply patches and upgrade software. There's license fees that you have to pay, maybe database licenses or web server licenses. There's lots of maintenance. You have to predict how much traffic you will see, and you have to plan for that and provision new servers in time. So we developed Google App Engine to give you essentially the cloud development in a box. We have an SDK, which you saw earlier today, where you can easily create an application, deploy it. And then when you deploy your application to the cloud, everything's in the box. The hardware's there, the software's there, the operating system, the Java or the Python runtime environment. We have a number of services. Really, we take care of everything. All you do is you take your code, you upload it to App Engine, and you're done. We take care of the rest. Now I want to talk a little bit about reliability and scalability and how it's traditionally done. What we do is we set up our production environment. We have our web server and our database server, and it's all working fine. But we're a little bit worried that if something happens to the server, that our website will be down. So the way you do it in rocket science is you have a second computer. And now we have redundancy. We have our primary server and our backup server. But this is not really very scalable. Now we have two machines to maintain, and we have to keep them identical. And when one fails, the other one has to take over. So there's a way that we have to figure out to make that failover happen seamlessly. Now, we look at kind of the failure in a different way. We host a lot of servers at scale. We have data centers full of machines. And when we look at it, we look at a single server, and we say, usually it's a few years between random failures. If I take a computer under my desk, and I turn it on, and I just work with it, maybe every 2 or 3 years the machine will crash for some strange reason, and I have to restart it. But if I have a rack of servers, then every few months at least one of those servers will fail. If I have a data center full of servers, it's probably only going to be minutes between failures. So there will be machines dying in the data center all over the place all the time. That's an entirely different way of dealing with software and server. Instead of building one big reliable server and then a backup, now you have thousands of machines with one of them dying every couple of minutes. So you can't sit there and fix them and fix that one. You need to hire an army of people. So you have to design software to be fault tolerant. And once you do that, then you gain a lot of freedom. Just like RAID for disk drives gives you freedom. Instead of having one disk with all your data and then when it fails you're down, you create multiple disks with copies of the data. So when one disk drive fails, you pull it out, you grab a new one, stick it in, and the data syncs up, and the whole platform keeps running. You do the same thing with servers. And the freedom it gives you is to think differently about scalability. Remember when we built that one server that was running just fine? And then our user base grows and our website becomes more popular, so we need a bigger server. But we're really putting demands on this machine, and so we need to grow it again. And we buy the biggest server that we can buy. And then we run out of capacity again. The server's running hot. There's nothing more we can do to buy a bigger machine. A better way to approach scalability is to take that one server that's very happy and just add another one. And then when we need more scalability, we just add more servers. And they all can run really fast. And anytime we run out of capacity, we just add more servers. We do the same thing in App Engine with the data store. Rather than having one database that grows and then grows to the point where it has to break, we start with one server, and as you put more data into it, we add another server and we add more servers, and they all run happily. So I'd like to talk about some of the features of Google App Engine that is built with this model in mind, with this model of scalability, where we just add more servers and more disks, and we scale out horizontally instead of vertically. When we built Google App Engine, we had 3 tenets in mind. We wanted it to be very easy for you to build applications, very easy to maintain those applications in the cloud, and we also wanted it to be easy to scale. So when more users show up and you become more popular, that you don't have to create a new database architecture, that you don't have to create a new web server architecture. When you deploy an application on App Engine, you're on the same architecture when you're the smallest app as the biggest application on App Engine. Now today, App Engine is about 100,000 developers that have built over 250,000 applications, and each day the platform serves about 250 million page views. So that gives you a sense of the scalability. We have quite a few people using App Engine. Here are some of the prominent names. Some of the bigger ones tend to be the social applications, though. These are the ones that go viral, where I like the application, so I tell it my friend, and he tells 2 friends, and they tell 4 friends, and very quickly almost everyone is using it. Buddy Poke is an example of a social application that has scaled to, I want to say it's about 40 million users now. So they run on Google App Engine, and all 40 million users are able to access their application. And they grew out, obviously, they started at one point with 1 user. Now the same thing could happen with your application. Now in the US we had, President Obama had an open town hall. He asked citizens to submit questions that he could answer, and then people could vote on which questions were the most popular. This was a 2-day event, and here you see a traffic graph. This is the App Engine traffic for Google Moderator for that 2-day period. And what's interesting is right at the deadline, you see a spike at the top where it's about 700 QPS, 700 requests per second. That was the highest load that the platform saw. But really what's much more interesting is how this graph goes up and down, up and down. That when this event is listed on a homepage of a major news organization or search engine, traffic goes up. When it's nighttime, traffic goes down. There's fewer users online. Now, if you had to build this the traditional way with servers, you would have to guess the 700 number. And if you guess too high, you would build too many servers and have extra capacity. If you guess too low, your website wouldn't be able to handle the traffic. And even if you guess the right number, in the downtime, you would have lots of idle capacity that's wasted. And with App Engine, the platform automatically scales up and down based on traffic. So when you see more traffic, we allocate more servers to your application. And then when traffic dies down, we remove those servers and give them to other users. As you saw this morning, it's very easy to deploy those applications. You click deploy, enter your password, upload your code, and you're ready. Your application is running. We have 2 languages that we support natively on the platform. There's Python, and this year we launched Java. And because we're running a real Java VM, there's a number of other languages that will run with varying degrees on App Engine as well. We have Scala, JRuby, Groovy. There's even Quarkus has provided a PHP capability. Now the one that runs natively and supported is Java, but these others are ones that the community has kind of gathered around and started to work on. Now with Java, we are really able to focus on standards. So you can write an application entirely using open Java standards and deploy to App Engine or deploy your application to another environment. So that gives you choice. Now sometimes you may not want to store all the data in the cloud. Maybe you have existing data that lives behind the firewall in a corporate environment, and you want to leave that data there, or you need to. For that, we need to federate, which is we need to take the data in the cloud and the data behind the firewall and let them work together without putting them in one place. For that, we have a little product called Secure Data Connector. This allows you to connect the cloud and your servers behind the firewall with a secure connection so that users can access your application in the cloud and still get to the data that lives behind the firewall. App Engine is always free to get started. There are about 5 million page views worth of traffic is free if you have a well-optimized website. It's a rapidly evolving platform. Just in the past, I'd say 18, 19 months or so, we've released really major features almost every month. And we do this because we're able to leverage existing Google services and infrastructure. And we plan to continue this. I don't think we're slowing down anytime soon. So that's just a little introduction on App Engine and the capabilities. Now I want to talk a little bit about Google Web Toolkit. You saw earlier today Google Wave, which was built with Google Web Toolkit, which shows you how you can build really powerful, interesting applications in Java, compile them to JavaScript so they run in any browser. Google Web Toolkit will take your Java code and it will compile a different version of your application for each browser so that you don't have to deal with all the cross-browser quirks. We compile it to JavaScript, HTML, and CSS, again, so there's no plugins. It just works natively. Now, I don't know if every one of you has heard of Google Web Toolkit before today, but it's actually been around for quite some time. We launched it in May of 2006, GWT 1.0. And if you have tried it, and you tried one of these earlier versions, you might be really surprised how far it's come in such a little time. Right now we're working on the 2.0 release, which should be out before the end of the year. And it really has an amazing set of features. It has a lot of features that were needed by the Google Wave team and allowed them to do some of the great things that they have done. So if you've tried it before, definitely come back and try it again. Now this is a long mission statement, and you don't need to read all of it. But this is the Google Web Toolkit mission. And what's important here is that we always focus on users. Users first. Now you also hear me talk a lot about developer productivity. And that is the secondary. We want you to be more productive as a developer so you can build better user interfaces for your users, build more powerful applications. So Google Web Toolkit has kind of two modes of operation. The most important one is what we call production mode. This is where we take the Java files that you create, all your source code, and we compile it to JavaScript, HTML, and CSS, and it just runs in the browser, any browser. But it's also important that you have that developer productivity. You want to be able to write your code, hit refresh in the browser, and do a quick test and see that it worked. So for that, we have another mode It's called development mode. Again, we take a real browser, and we take the Eclipse IDE, although you could use something else if you like, and we launch your application inside of a Java virtual machine. So you get all the Java tooling, you get all the integration with Eclipse. And inside the JVM, we launch a web server. This is just a regular web server that can serve HTML, CSS, and JavaScript files and other images. We also launch a code server. This is a special server that can take Java code and serve it to the browser so that it can run JavaScript. And then inside the browser, only for development, we have a special plugin. Now this plugin lets you run Java while executing JavaScript. Your users don't need it. This is only for development. So to summarize GWT, we focus on productivity for developers. But great languages, great IDEs, tools and libraries, people, just the ecosystem that is around Java, and performance for your users. Things like perfect caching, we'll get into, whole program optimization. Because we compile your application, we can look at the whole program and make optimizations that other libraries can't. So I want to talk about why Java is such an important language that we choose. So we have the Java language, runtime and tools, and there's rich libraries, which means we can leverage existing work. Instead of rebuilding it, we can use a library and we can just drop it in, which means we can deliver faster. We spend less time writing code. Java also provides great IDEs, great development environments, which really increases developer productivity. It makes you work faster, make you work more efficiently. And that allows you to iterate faster. You can deliver a new version sooner. Java is also a static language. And that means that at compile time, you can make certain assertions. You can check that certain things are true. And that's not true of other languages that are dynamic. Okay, back, sorry. That means we can do compile time, validation of your code. We can check things and catch bugs that normally you'd have to wait for runtime. So that lets you find things sooner. And we can do very aggressive optimizations. We can, and I'll get into those later. But that ultimately gives us fewer bugs and faster code. Now if we add this all together, what we get is an improved user experience. And that's really what it's all about. Better web applications for our users. So I talked about powerful IDEs. That means you can do things like code completion. And it's very important that Java is a static language. Here, if you can read it, there's a button class, and someone has hit Command space or Control space to see a list of available methods on the button class. Now the Eclipse IDE can show me those methods because it can look at my source code and see that this is a button and only a button. And so it can show me all the methods that go with the button class. If this were a different language, if this were JavaScript, for example, then this wouldn't be possible. Because in JavaScript, a variable can change its nature. If you have a variable A, you can assign it a number, and then you can reassign it to a string, and then reassign it to an object, and then you can turn it null, and then undefined, and put it back to a number. That means that your IDE can't possibly know what all the possible methods are, because it can't know the type of the variable. So it's important that Java is a static language. There's another reason that static language is important, is here I have a little piece of code that tries to find the maximum value for inside an array. Now, if you look at this, and I hope you can read it, there's actually a bug in this code. But it's pretty hard to find. Now, let's walk through the flow. So we take the array, and we take the very first value, so values 0, and then we loop through the remaining values, and we try to find a value that is higher than the value found so far, greater than the maximum. If so, we find the new maximum, and then at the end, when we loop through all the values, we return the maximum. So this function is trying to find the biggest number in a list of numbers. But it turns out there's a bug here. And the hint is that JavaScript is a dynamic language. And I'll show you the same code. If you haven't found the bug yet, I'll show you the same code in Java in the IDE. And without compiling it, the IDE has already told us where the bug is. I've misspelled the variable maximum. There's a little n instead of an m. Now in Java, this is not valid, because I didn't declare the variable maximum. In JavaScript, however, this is perfectly valid code. What I'm doing inside the loop, in the very inner statement, is I'm actually assigning a value to a new variable that is never used. So this is a bug that's really hard to find, and the compiler can't even tell me about it. But using Java, the IDE will tell me the moment I type it, before I ever run it, before I ever test it, before a user ever sees it. So this is really where some of the productivity gains come from, and why Java is an important language. Now, GWT tries to help you in many ways to create faster applications. To deal with the latency issue, we have a feature that we kind of call perfect caching, where we try to cache the resources in your application forever. And then we have client bundle, which can take multiple images and put them together in one film strip. Or it can take multiple CSS files and merge them together. It can take a CSS file and take all the comments out and all the white space and shrink it up together and make it more efficient. To deal with the number of connections, we use data URLs so that we can avoid a fetch. We also use the client bundle to take 5 round trips and turn them into 1, for example. To limit bandwidth, or to deal with limited bandwidth, we have a feature called developer-guided code splitting, where we take your application and we figure out which code runs that you want to run initially, and that's the only code that's downloaded when the user opens the application. And then when the user accesses additional functionality, additional pieces of JavaScript are downloaded. And then to deal with browser performance, we have very aggressive optimization techniques. And we use deferred binding. This is the mechanism whereby we can produce different code for IE and for Firefox and for Safari while using a common code base. So I want to show you a little bit what Client Bundle does. And it basically gives you sprites for free. Let's say I have an application with 11 images in it. Now, if you remember from the latency slide, this means 11 round trips to the server. 160 milliseconds, 160 milliseconds, 11 times. That's quite a bit of latency. What if we could take all these images, bundle them together into one image, and then that would be one HTTP fetch? We could save 10 times 160 milliseconds. That's 1600 milliseconds, or 1.6 seconds. That's a huge savings. My application can now start 1.6 seconds faster. And it's the same bandwidth requirements, it's the same images, the same application. All I did is took 11 images and bundled them together into a single sprite. But I get other efficiencies as well. Each one of those 11 images has some overhead associated with it. If you save the image in Photoshop, for example, the header in the image contains that information, some comments. Each of these images contains a color palette to show which colors exist in it. And not all the images may be compressed optimally. So if we actually add up all the bytes in those 11 images, we get this big stack of about 21K. Just by combining the images, we actually get a smaller image that's only about 7K. So we've done nothing but bundle these images together, and we've gone from 11 HTTP round trips to 1, and we've gone from 21K to download to 7K. Now you can do this in a traditional JavaScript application, but it's a lot of work. And GWT makes it really easy. All you do is identify these 11 images in a file, and then GWT does all the work for you, bundling them together. Now I want to talk to you about perfect caching. Perfect caching is a mechanism whereby we can take resources in your application, such as images or the actual JavaScript of your application, and cache them forever. Now, if you know how a web browser works, usually when you visit a web page, when you go the first time, the browser has to fetch all the images. So there's lots of round trips. Now all those images sit in the browser cache. Now let's say the next day, I go again to the same website. I type in the same URL. And what the browser does is it talks to the server and it says, has this URL been updated yet? And the server says, not modified. And the browser says, OK, I'll take the version from the cache. And says, oh, I have 11 images. Talk to the server. Server, has this image been updated? Not been modified. OK, I'll use the one from the cache. Server, has this image been modified? No. OK, I'll take the one from the cache. So even though the entire application is stored in the browser cache, the browser is still talking to the server and still causing those HTTP round trips and still paying that latency penalty, 160 milliseconds every time, for these images that are in the cache. What we really want is, when an image is in the cache, we want to use it without talking to the server. So that's what perfect caching is about. So what you see here is the very top box, this green one, index.html. That's your main HTML page. And it contains a script tag. The script tag points to the second green box there, foo.nocache.js. This is a little tiny script that GWT creates for you, which is called the launch script. It's the one that detects which browser you're using. If you're IE, then it loads one version of the blue application. If you're in Firefox, it loads a different blue version. If you're in Safari, it loads yet a different blue version. The blue box there is your entire application. This is a really big, meaty file. This is all the JavaScript in your application. It's some of the inline images. And then this blue application also points to resources. For example, there in the bottom, the red one is the sprited image. Those 11 images kind of bundled together. Also other resources, that yellow box shows you multiple resources combined. Now, what GWT does is when it generates your JavaScript application, when it generates that big blue box of code, it calculates a checksum, an MD5 checksum. And then it creates a file with that checksum.cache.html. And then you configure your web server to cache these files forever. Now, if you make any changes to your application at all, even if you change 1 byte of code, you'll get a different checksum. And so the file name on the blue file changes. So now you can have, what we like to say, you can have your cake and you can eat it too. You can have the blue, red, and yellow. These resources are cached forever, but if you make any changes to your application, then that second green box points to new file names that are downloaded. So users get new applications as soon as you deploy them, but existing users don't have to pay the extra round trip. Now I'll talk a little bit about deferred binding, about doing a different implementation for each browser. You see here across the top, the kind of the yellow bar, there's a way to set the inner text inside an HTML element in a web browser. This is a simple method called set inner text, and it works on all major browsers. So it's a natural choice. But if you measure, it turns out that this is not the fastest way to do it in any browser. It's kind of a poor choice. In fact, if you follow the green boxes, you'll see that the fastest way to do it is different in each browser. And what GWT does is it allows you to use the green option in each case. And so you get a 14 here, 29, 32, and 39% increase in performance for that little application without having to pay the cost. Because Firefox users only download the version of your code for Firefox. Safari users only download the Safari version of the code. So there's in this case, 4 different versions of your application sitting on your server, and users only download the one that they need. Now this graph, I kind of alluded to before. This is a graph measuring the code size of the initial download of Google Wave as it was being developed. So we started very low, and over time, engineers were submitting more and more features and more capabilities and letting Wave grow. And you see that very quickly, the initial download size grew to almost 1.5 megabytes of JavaScript. That is a lot of JavaScript. If you have to wait for that to download, that's a long wait. So that's not a good idea. So what GWT did is it introduced a feature called developer-guided code splitting. This is where in your application, you indicate in specific points code that can be deferred or delayed to later. And as soon as the Wave team used this capability, they saw about a 7x decrease in the initial download size. Now the entire application is still 1.5 megs, but when I first load Wave, I don't need all the functionality. I need some of the functionality. And then as I click on different features, or maybe in the background, Wave can fetch additional JavaScript files. So I don't have to wait for those, but they can become available. So now with Google Web Toolkit and Google App Engine, we have a complete Java development stack for the web. Java is really useful to develop on the client and the server for another reason. And that's we can use a common interface and a common set of code. We can share code between client and server. We can have data transfer objects or POJOs that can be used on the server when they're running in Java VMs as bytecode, or used on the client when the Java has been translated to JavaScript. And Google Web Toolkit will take care of that translation for us. So this is an example of a spelling service for suggesting words. So you know when you go to, say, google.com and you start searching for something, and you get a list of suggestions. As you type, the suggestions change. This is an example of the interface that a servlet might implement. It takes as a parameter the word that you're typing, and it returns an array of suggestions to put in the pop-down box. By having this interface and a common development language, we can use this code on both client and server. That makes us much more productive as developers and makes life simpler. You saw in the demo today a Google plugin for Eclipse with lots and lots of capabilities specific to Google Web Toolkit and some specific to Google App Engine as well. One of the things I pointed out today was debugging in the browser, where you can set breakpoints. If there's one quote for you to remember, though, is in Google Web Toolkit, the fastest code is that which does not run. That seems like a kind of a funny quote, but it refers to the compiler optimizations that the GWT compiler can make. When GWT is looking at your code, and because it's Java and it's a static language, it can see the methods that you call and the ones that you don't call, and it can take the ones that you don't call and remove them from the application so that the user doesn't have to download them. It can also look at the code and see that maybe you're calling one method that's really simple, and it would be much more efficient to take that method and inline it at the call site. That way, the user doesn't have to pay for the method call. Also, if you have maybe an if-else block, you know, if debug equals true, do this, else do that. And the GWT compiler can look at your code, and it can know that maybe the debug flag is set or not set. And so it can take the if statement that normally would have to be executed, if this, else that, and it can only keep the code that is actually being used. So that makes the code faster and lighter. So all this code is there in your development environment, but it's not there for the user. And you can start to rely on this. In fact, if you look at the Google Web Toolkit APIs, you see that we have many layers of abstractions. When you make a call to make a change in the DOM, if you follow that through with the IDE, you'll see that this method calls this method, calls that method, which actually does something. That's not normally how you would want to write code, because the user would have to pay for this method invocation, that one, that one, that one, and then execute the code. But when the GWT compiler looks at your code, it sees all those method hoops, and it realizes that it can simply inline the code and make it all disappear. So at the end of the day, you get to have your abstractions, you get to write the code that makes sense for you, that makes your site very maintainable, very testable. But your user doesn't have to pay for all that code. They only download the pieces they need. Now these are just a hint at some of the compiler magic that we do. We have conventional compiler optimizations and very unconventional ones, because GWT is a little bit different than other toolkits. The Java transformations we can do is, for example, the dead code elimination, where we take code that's not executed, that we know is not executed, remove it. The method inlining I talked about, and then constant folding and propagation. If I say A equals 4, and then somewhere else B equals A plus 2, I know that B is 6, and so I can just inline it in the browser. And that can have some efficiencies in the code as well. For JavaScript, once we've output the JavaScript in the application, we have other tricks as well. It turns out that, the web browser and the server, they don't usually transmit plain text. They actually use gzip compression to send data over the wire. Now if you take JavaScript, regular JavaScript, and you gzip it, you get a certain compression ratio. You know, maybe you compress down to 85%, or maybe it's 40%. It depends on your application. And what we've discovered is that just by rearranging the JavaScript in the application and making subtle changes to the compiler, we can improve the compressibility of the JavaScript without actually making it smaller. So we started with JavaScript that was this size, and we replaced it with the equivalent JavaScript, same size, but with pieces moved around. And actually this compresses this much, but this new one compresses that much. And it's kind of interesting to look at that, but it's a simple matter of understanding how gzip works. Gzip looks at repeated strings and tries to encode them more efficiently. So for example, when we have JavaScript methods in our application, we might have a function call that has 3 parameters, so A, B, and C. But we might have another function that has B, C, and D. Those don't compress very well because there's 2 different strings. But if we simply change the parameter names from A, B, C, and then in a different method also A, B, C, and then we put those 2 functions close together, the gzip compression will actually see those 2 strings and compress them a lot better because they're close together and because the strings match. So with just little tricks, we make the actual download for the user much smaller. Now, in closing, I want to point out a couple of URLs. These are the main pages for Google Web Toolkit and Google App Engine, where you can learn more. My contact information, feel free to send me an email afterwards. But also, if you have questions, either now or come visit us in the office hours, which are posted. Thank you very much. Okay. So, any questions? Raise your hand. Let's see. Yes. So the question is, what parts of a Java framework do we support? That's a good question. One of the biggest constraint that you will see is that the Java code has to be compiled to JavaScript. And so you have to, any framework that you use has to play by the same rules that JavaScript plays. So JavaScript is a single-threaded environment. So any Java framework that needs to create multiple threads isn't going to run natively in Google Web Toolkit. Also, the browser has other sandbox restrictions, like it's not possible to have native access to the file system or to open network sockets. So frameworks that do those sorts of things, those pieces won't work. We've emulated quite a few of the Java APIs for inside the browser, but not all of them. There is a list on the website. So the short answer is that generally Java code just works, but frameworks that try to interact with other systems won't work just because they won't work in the browser. Okay. Yes? Okay, so the question is, what does the integration look like with other JavaScript libraries like jQuery? And the answer is kind of twofold. First, Google Web Toolkit plays really well with other libraries. They can sit side by side, and you can certainly use jQuery or Dojo, Scriptacular, something else with Google Web Toolkit, but you won't necessarily get all the benefits of Google Web Toolkit. GWT does the best work with optimizations when it can take Java code and turn it into JavaScript. When you use, for example, jQuery or some other library, it stays JavaScript and the size is fixed. And so as an in-between state, you can use both, but long-term, you get the most benefit if you use pure GWT. I think we have to close for the next session. So if you have more questions, please come find me in the office hours. Thank you again.